Settle into the sleepy mind channel, and tonight we will explore the Devonian period. If you enjoy videos like these, feel free to like and subscribe, as new videos are posted each week. The Devonian period began about 419 million years ago. It belongs to a distant span of Earth's history that existed long before animals walked on land or forests covered the continents. At this time, most life exists in the ocean, and the land above is largely bare and rocky. The seas are warm and shallow, spreading across wide continental shelves where sunlight reaches the bottom. Light passes through clear water and settles across sand, stone, and early reef formations. These conditions allow life to grow across large areas, creating environments filled with constant activity. This period is known as the Age of Fishes because fish diversify rapidly and spread into nearly every available space. New forms appear with different body shapes, sizes, and ways of feeding. What begins as variation quickly becomes competition, and competition drives further change. Early jawed fish move through the water with a level of control that did not exist before. Their mouths close with force, allowing them to grasp, tear, or crush prey rather than filter or scrape. This development changes how organisms survive, and it reshapes the structure of marine ecosystems. The development of jaws comes from structures that originally supported the gills in early fish. These structures begin to change, forming joints and muscles that allow the mouth to open and close with force. Over many generations, this change creates a completely new way of feeding that spreads across multiple groups. With this change, organisms that can bite gain access to new food sources that were previously unavailable. Hard shells, larger prey, and moving targets become possible to capture and consume. This expands the range of feeding strategies and increases competition within the ecosystem. As more species develop jaws, other organisms must adapt to survive within this new environment. Some develop thicker protective coverings, while others rely on speed or group behavior to avoid being captured. This creates a cycle where each improvement leads to another response from competing species. The seafloor is covered with life, including organisms that grow in place and others that move slowly across sediment. Reefs form from corals and stromatoporoids, building large structures that provide shelter and feeding areas. These reef systems support increasing biodiversity, as many species depend on them for protection and access to food. Reef systems during this period can grow to large sizes, forming complex structures that support many different forms of life. These environments include areas for feeding, hiding, and reproduction, allowing species to interact in close proximity. The physical structure of the reef creates many small habitats within a larger system. Different organisms occupy different parts of the reef, depending on their needs and abilities. Some remain close to the surface, where light is strongest, while others stay deeper within the structure, where protection is greater. This separation allows many species to exist within the same area without directly competing for the same resources. Small fish gather in groups and move together to reduce the risk of being eaten. Their movement is coordinated, with individuals adjusting direction quickly when nearby pressure changes. This behavior allows them to react as a group, rather than as separate individuals. Larger fish move differently, using steady motion and controlled positioning to access prey. They do not rely only on speed, but on timing and placement within the water. This creates a balance between fast movement and controlled presence within the ecosystem. The oceans remain warm and widespread, with high sea levels covering large portions of the planet. Shallow marine environments extend across broad regions, providing stable conditions for life to expand. These conditions allow ecosystems to grow more complex over time. Continents are arranged differently than they are today, with large land masses slowly moving toward one another. The supercontinent Euramerica begins to form, while Gondwana remains a massive southern landmass. These large-scale changes will eventually affect ocean circulation and climate. Plankton drift through the water and serve as a primary food source for many organisms. Their presence supports larger populations of fish and other marine life. Each level of the ecosystem depends on another, forming connected systems that continue to expand in complexity. Plankton populations increase as conditions remain stable and nutrients are available in the water. These small organisms form the base of the food web and support larger species at higher levels. Changes in plankton levels can affect the entire ecosystem, making them an important part of marine life. As plankton numbers grow, fish populations are able to increase as well, leading to more complex interactions between species. Predators depend on these food sources either directly or indirectly, linking all levels of the ecosystem together. This connection means that changes at one level can influence many others. Some fish develop stronger skeletal systems that improve movement and stability in the water. Teeth become more specialized, allowing different species to target different types of food. These adaptations reduce direct competition by allowing organisms to use different resources. Other fish rely on speed and quick changes in direction to avoid predators. Their bodies are shaped for rapid movement, allowing them to escape when threatened. Survival depends on reacting quickly to changes in the surrounding environment. As these changes continue, marine food webs become more complex and interconnected. Each new adaptation creates pressure for further change in other organisms. This ongoing interaction drives the rapid diversification seen during this period. The Devonian seas support some of the largest fish that had appeared up to that time. Increased food availability and stable environmental conditions allow organisms to grow larger. Size becomes another advantage within an increasingly competitive environment. At the same time, earlier forms of fish without jaws begin to decline. Jawed fish outcompete many of these older groups, changing the balance of life in the ocean. This shift marks a major transition in the history of vertebrate evolution. Cartilaginous fish, including early sharks, begin to appear and diversify during this period. Their bodies are built differently, using flexible cartilage instead of bone. This allows for efficient movement and introduces another successful strategy within the ecosystem. Bony fish also continue to diversify, becoming one of the most successful groups of vertebrates. Their structures allow for a wide range of movement and feeding behaviors. Many modern vertebrates can trace their ancestry back to these early forms. Across the ocean, life continues to expand and compete within stable but demanding conditions. These conditions push organisms to adapt as pressure increases. Every change creates new opportunities and new pressures, shaping the direction of evolution. The result is a marine world that is more active, more varied, and more interconnected than anything that came before it. These developments lay the foundation for future changes that will extend beyond the ocean. Life is beginning to move toward new environments, and the conditions for that shift are already in place. The Devonian seas now support predators that move with strength, control, and efficiency. Among the most notable of these is Dunkleosteus, one of the largest and most powerful fish of this period. Its presence represents a major shift in how predation works within the ocean. A large armored fish, known as Dunkleosteus, does not rely on sharp teeth like many modern predators. Instead, its head and upper body are covered in thick plates of bone that provide protection and structural strength. Its jaws are formed from solid, bony plates that act like blades, closing with enough force to cut through prey. Some individuals of Dunkleosteus may have reached lengths of over 20 feet, making it one of the largest predators of its time. Its size alone gives it an advantage, allowing it to overpower smaller organisms without needing to rely on speed. This combination of size and strength places it near the top of the food chain. The evolution of jaws allows predators like Dunkleosteus to interact with their environment in new ways. Jaws originally developed from structures that supported the gills in early fish, gradually forming hinges and muscles that allow controlled movement. This transformation creates a feeding system capable of gripping, cutting, and crushing. With these adaptations, Dunkleosteus is able to target a wide range of prey, including armored fish and other large organisms. Its feeding strategy does not depend on chasing small, fast targets, but on selecting prey it can overpower. This allows it to conserve energy while maintaining dominance within its environment. Placoderms, the group to which Dunkleosteus belongs, are among the first vertebrates to develop true jaws. These armored fish thrive during the Devonian, occupying many roles within marine ecosystems. Their success is tied directly to their ability to feed more effectively than earlier jawless species. The presence of large predators changes how other organisms behave within the ecosystem. Smaller fish must remain in motion or stay near protective structures to avoid being captured. This constant pressure shapes movement patterns and influences where different species are able to survive. Armored fish develop thicker protective coverings to reduce the risk of being damaged during an attack. These coverings can deflect or absorb force, increasing the chances of survival during encounters with predators. Protection becomes an important strategy alongside speed and group behavior. Not all fish rely on heavy armor, and many species develop alternative ways to survive. Some become faster and more agile, allowing them to escape quickly when threatened. Others rely on coordination within groups, using synchronized movement to confuse predators and reduce individual risk. Early sharks begin to appear during this period, introducing a different approach to predation. Their bodies are built from cartilage rather than bone, allowing for lighter and more flexible movement. This design supports efficient swimming and rapid changes in direction. Unlike heavily armored placoderms, early sharks depend more on speed and sensory awareness. They are able to detect movement and respond quickly, making them effective hunters in open water. This creates a contrast between strength-based predators and speed-based predators within the same environment. Bony fish continue to diversify alongside these groups, developing a wide range of feeding strategies and movement patterns. Their skeletal structures allow for flexibility and control, supporting both slow and fast forms of motion. This diversity helps them occupy many ecological roles. The interaction between these different groups creates a complex food web where no single strategy dominates completely. Strength, speed, protection, and coordination all play roles in survival. Each adaptation provides advantages in certain situations, but none guarantee complete safety. As predators become more effective, prey species must respond with their own adaptations. This ongoing cycle drives further evolution, leading to increased specialization among organisms. The Devonian becomes a period of rapid change as each group adjusts to the presence of others. Some fish develop crushing plates that allow them to feed on hard-shelled organisms. This opens access to food sources that are not available to other species. By targeting different resources, these fish reduce competition and increase their chances of survival. The structure of the ecosystem becomes more layered as these feeding strategies expand. Organisms occupy different levels based on what they eat and how they obtain food. This layering increases the overall stability of the system while also making it more complex. Large predators, like Dunkleosteus, influence not only individual prey, but entire populations. Their presence can limit the number of certain species, preventing any one group from becoming too dominant. This helps maintain balance within the ecosystem. At the same time, the decline of earlier jawless fish continues as they are outcompeted by more advanced species. Without the ability to bite or defend effectively, many of these organisms are unable to survive in changing conditions. Their reduction marks a clear transition in vertebrate evolution. The Devonian Ocean now contains multiple types of predators that operate using different strategies. Some rely on strength and armor, while others depend on speed and flexibility. This variety increases competition and drives further innovation. Environmental conditions remain stable, with warm temperatures and high sea levels supporting widespread marine habitats. These conditions allow organisms to expand and interact across large areas. Stability at the environmental level supports rapid biological change. Plankton continues to support the base of the food web, providing energy for smaller organisms that are then consumed by larger ones. This flow of energy connects all levels of the ecosystem. Without this foundation, the complex structure of marine life could not be sustained. As interactions between species increase, the ecosystem becomes more dynamic and interconnected. Each change affects multiple levels, creating a network of relationships that continue to evolve. The Devonian Ocean is no longer a simple environment, but a system of constant adjustment. The presence of large predators, including Dunkleosteus, represents a shift toward more active and force-driven ecosystems. Organisms must respond quickly to survive, and this pressure drives further development. The pace of change continues to increase. These developments set the stage for even more complex interactions in later periods. The foundations of modern marine ecosystems are being established during this time. The patterns of predation, adaptation, and competition will continue to shape life moving forward. The Devonian Ocean continues to expand in complexity as more groups of fish develop new forms and strategies. Placoderms remain common, but they now share space with other emerging groups that compete for similar resources. No single group dominates completely, and the balance continues to shift as new adaptations appear. Cartilaginous fish, including early sharks, become more noticeable as they diversify into different shapes. Their skeletons are made of cartilage, which allows for lighter bodies and more flexible movement in the water. This structure supports efficient swimming and gives them an advantage in open environments where speed matters. These early sharks do not all look the same, and many have body shapes that differ from modern species. Some have longer bodies, while others develop unique fin structures that affect how they move. This variation shows that different approaches to survival are being tested within the same environment. Unlike heavily armored fish, these predators rely on movement and awareness rather than protection. Their ability to change direction quickly allows them to respond to shifting conditions and avoid obstacles. This makes them effective hunters in areas where visibility and reaction time are important. Bony fish continue to increase in number and diversity, becoming one of the most adaptable groups in the ocean. Their skeletons provide both strength and flexibility, allowing for a wide range of motion. This allows them to occupy many different ecological roles within the system. Some bony fish develop specialized teeth that match the type of food they consume. Sharp teeth allow for gripping and tearing, while flatter surfaces are used for crushing harder materials. These differences reduce direct competition by allowing species to focus on different food sources. Other species develop body shapes that improve speed or maneuverability, depending on their environment. Fish that live near reefs may require precise movement, while those in open water rely on sustained swimming. These differences allow species to survive in specific conditions without overlapping completely. The ocean now supports a wide range of feeding strategies that create a layered food web. Organisms feed at different levels, from plankton to large predators, forming connections that link all parts of the ecosystem. This structure becomes more stable as it becomes more complex. Plankton continues to play a critical role as the base of the food web, supporting the growth of many other species. As plankton populations increase, they allow higher levels of the ecosystem to expand as well. This creates a steady flow of energy through the system. In areas where plankton is abundant, fish populations increase and attract predators that depend on them for food. This leads to concentrated areas of activity where multiple species interact at once. These zones become centers of feeding and competition. Some fish develop crushing plates instead of sharp teeth, allowing them to feed on hard-shelled organisms. This adaptation opens access to prey that other species cannot easily consume. By using different feeding methods, these fish reduce direct competition within the same habitat. Marine food webs become more complex as each species develops a specific role within the system. These roles depend on feeding behavior, movement patterns, and environmental conditions. The interactions between these roles create a dynamic and constantly changing environment. Fish of different sizes occupy different levels of the ecosystem, from small species that feed on plankton to larger predators that feed on other fish. Size becomes an advantage in some situations, but it also requires more energy to maintain. This balance influences how species grow and survive. Some of the largest fish seen so far appear during this period, supported by abundant food and stable conditions. These large organisms influence the behavior of smaller species, shaping how they move and where they gather. Their presence affects the structure of the ecosystem as a whole. Despite this growth, not all groups are equally successful, and some begin to decline as conditions change. Jawless fish continue to lose ground as jawed species become more efficient at feeding and defense. This shift represents a clear transition toward more advanced forms of vertebrate life. At the same time, ecosystems near reefs continue to support high levels of biodiversity. These areas provide shelter, food, and opportunities for interaction among many species. The complexity of reef systems makes them important centers of activity within the ocean. Fish that live near reefs must be able to navigate tight spaces and respond quickly to threats. This leads to the development of more precise movement and improved control. These adaptations allow them to survive in environments that require constant awareness. In contrast, fish in open water rely on sustained movement and efficient swimming to survive. These environments require endurance and the ability to travel longer distances in search of food. Different habitats continue to shape how species evolve and behave. The Devonian Ocean now contains multiple overlapping systems that function together as a larger whole. Each region supports different species and interactions, but all are connected through the movement of organisms and the flow of energy. This creates a network that continues to grow in complexity. As these systems develop, interactions between species become more frequent and more varied. Predation, competition, and cooperation all contribute to the structure of the ecosystem. Each interaction influences how species adapt over time. The continued diversification of fish during this period leads to levels of variety not seen before in Earth's history. This expansion sets the stage for future evolutionary developments that will extend beyond the ocean. The Devonian becomes a key period in the development of modern ecosystems. Changes that occur during this time will have lasting effects on the direction of life on Earth. The development of new feeding strategies, body structures, and movement patterns creates a foundation for future species. These patterns will continue to evolve in later periods. The ocean remains a place of constant activity, where movement and interaction define survival. Every organism must respond to changes in its environment, and those that cannot adapt begin to disappear. This ongoing process drives the continued evolution of life. As the Devonian progresses, the increasing complexity of marine ecosystems prepares the way for new transitions that will extend beyond the water. The conditions that support life in the ocean are beginning to influence what will eventually happen on land. During the Devonian, some fish begin to develop structures that will eventually support movement on land. These fish are known as lobe-finned fish, and their fins are different from those of most other species. Instead of thin rays, their fins contain strong internal bones and muscles that allow more controlled movement. These fins move in a way that provides support against the ground in shallow water. Rather than only pushing against water, they can press into soft sediment and create forward motion. This ability becomes important in environments where water levels change or where movement through dense vegetation is required. Over many generations, these structures become more developed and begin to resemble early forms of limbs. The bones within the fins align in ways that later correspond to major limb structures in land animals. This transformation takes place gradually, as each change builds on previous adaptations. One of the most well-known examples of this transition is Tiktaalik, a fish that shows both aquatic and land-related features. Tiktaalik has fins with internal bones that allow it to support its body in shallow environments. These features make it an important example of how movement begins to change during this period. A transitional fish known as tiktaalik also has a neck, which is unusual for fish, as most fish have heads that are directly connected to their bodies. This feature allows it to move its head independently, improving its ability to interact with its surroundings. Greater mobility provides an advantage when navigating complex environments. In shallow waters, the ability to lift the head and adjust body position becomes useful for both feeding and avoiding obstacles. These environments are often crowded with plants, sediment, and other organisms that require precise movement. Increased control allows fish like tiktaalik to move more effectively through these conditions. The development of lungs in some fish also plays a role in this transition. These lungs allow fish to take in air when oxygen levels in the water are low. This adaptation becomes useful in environments where water conditions change frequently. Lungfish, which still exist today, provide an example of this adaptation in modern species. They are able to survive in low oxygen environments by breathing air when necessary. This ability shows how early adaptations can continue to be useful over long periods of time. Freshwater habitats during the Devonian are rich with life and often contain dense vegetation. These environments create both opportunities and challenges for organisms that live within them. Movement through these areas requires strength, control, and the ability to respond to obstacles. In these habitats, fish must navigate shallow water, uneven ground, and changing conditions. Water levels may rise and fall, exposing parts of the environment at different times. This variability creates pressure for organisms to develop new ways of moving and surviving. The transition from fins to limbs does not happen quickly, but takes millions of years to develop. Each stage provides small advantages that allow organisms to survive in slightly different conditions. These changes accumulate over time, leading to more significant transformations. Early tetrapods begin to appear during the Devonian as a result of these changes. Tetrapods are vertebrates with 4 limbs, and they represent a major step in the movement of life onto land. These early forms still depend heavily on water, but they begin to explore new environments. An early tetrapod known as Acanthostega shows features that are suited for aquatic life. Its limbs contain digits, but it remains primarily adapted for movement in water. This suggests that limbs develop before full land movement becomes common. Another early tetrapod known as Ichthyostega shows stronger adaptations for movement on land compared to earlier forms. Its body structure supports more weight, allowing it to move more effectively in shallow or partially exposed environments. This represents a further step in the transition toward life on land. Despite these developments, early tetrapods still rely on water for many aspects of their survival. They depend on aquatic environments for reproduction and protection from predators. This means that their movement onto land is gradual and limited at first. The presence of limbs with digits allows for new types of movement that were not possible before. These structures provide support and allow organisms to push against solid surfaces. This ability becomes important as organisms begin to interact more with land environments. As plants continue to spread across the land, they create new habitats that can support different forms of life. These environments include areas with shade, moisture, and food sources that attract organisms from the water. The expansion of plant life plays a role in encouraging the movement of animals onto land. The interaction between aquatic and terrestrial environments becomes more complex during this period. Organisms begin to move between water and land, using features that support both types of environments. This creates new ecological relationships and opportunities. The Devonian marks the beginning of vertebrate life on land, even though the transition is still incomplete. Early tetrapods represent the first steps in a process that will continue in later periods. Their presence shows that life is beginning to expand beyond the ocean. These changes do not happen in isolation, but are connected to broader developments within the ecosystem. As marine life becomes more complex, pressure increases in aquatic environments. This pressure may encourage some organisms to explore new areas where competition is lower. The movement of life toward land is not a single event, but a gradual process involving many intermediate stages. Each stage reflects a balance between aquatic and terrestrial adaptations. This process continues to shape the direction of evolution. The Devonian period sets the foundation for future developments that will transform both land and sea. The structures that begin to form during this time will later support fully terrestrial life. These early steps mark the beginning of a major transition in Earth's history. As these organisms continue to adapt, the boundary between water and land becomes less defined. Life begins to extend into new environments, supported by structures that allow greater movement and flexibility. The changes that begin here will continue to influence life long after the Devonian ends. As life begins to expand beyond simple marine systems, the Devonian seas develop some of the largest and most complex reef environments in Earth's history. These reef systems grow over long periods, forming structures that support a wide range of organisms. Their size and stability allow many species to live in close proximity. Reefs are built primarily by corals and stromatoporoids, which grow slowly and form layered structures over time. These organisms create solid frameworks that provide surfaces for other life to attach and grow. As these structures expand, they become central features of the marine environment. The physical shape of a reef creates many different conditions within a single area. Some regions receive strong sunlight and support organisms that rely on light, while others remain shaded and protected. This variation allows multiple species to occupy different spaces without direct competition. Marine biodiversity increases significantly within these reef systems as more species adapt to specific conditions. Each organism fills a role based on its feeding strategy, movement, and environmental tolerance. This leads to highly structured ecosystems where interactions become more frequent. Fish that live near reefs must navigate complex spaces filled with obstacles and narrow passages. Their bodies and movement patterns adapt to these conditions, allowing for precise control and quick changes in direction. This ability becomes essential for both feeding and avoiding predators. Other organisms remain attached to the reef structure, filtering food from the water or growing in place. These stationary species depend on water movement to bring nutrients and oxygen. Their presence adds to the overall complexity of the environment. Reefs also serve as important feeding grounds where many species gather in search of food. Predators move through these areas, taking advantage of the high concentration of prey. This creates zones of intense interaction where survival depends on constant awareness. The stability of reef environments allows ecosystems to develop over long periods without major disruption. This supports the growth of large populations and the development of specialized roles within the system. As a result, reefs become centers of biological activity. At the same time, the surrounding ocean remains warm and widespread, maintaining conditions that support reef growth. High sea levels allow shallow marine environments to extend across large regions. These conditions provide the space needed for reef systems to expand. The interaction between reefs and open water creates transitions where different types of organisms meet. Species that prefer open environments move toward reefs to feed, while reef organisms may venture outward. These boundaries increase the number of interactions within the ecosystem. Some fish develop feeding strategies that are closely tied to reef environments. They may feed on organisms that grow on the reef surface or within its structure. This specialization allows them to take advantage of resources that are not available elsewhere. Other species use the reef primarily for protection, staying within its structure to avoid predators. The complex layout provides many places to hide and reduces the chances of being captured. This makes reefs important for the survival of smaller or slower organisms. As these systems continue to grow, they become more interconnected with other parts of the ocean. Organisms move between reef and non-reef environments, linking different ecosystems together. This movement helps maintain balance across the larger marine system. Despite their stability, reef systems are not isolated from change. Environmental conditions such as water temperature and nutrient levels can affect their growth and survival. Changes in these conditions may influence which species are able to thrive. The expansion of reefs contributes to the overall increase in marine life during the Devonian. By providing structure and resources, they support a wide variety of organisms. This makes them one of the most important features of the period. As biodiversity increases, competition within reef systems also becomes more intense. Species must adapt to specific conditions and compete for limited space and resources. This pressure drives further specialization and diversification. The presence of reefs influences the behavior of many species beyond those that live directly within them. Predators adjust their hunting strategies based on reef structure, while prey species use the reef for protection. This creates a dynamic relationship between different groups. Over time, these interactions lead to more complex food webs that connect many levels of the ecosystem. Each organism plays a role in maintaining the balance of the system. Changes at one level can affect many others, increasing the importance of each interaction. The Devonian reefs represent a peak in marine ecosystem complexity for this period. Their size and diversity set them apart from earlier systems. They provide a foundation for understanding how ecosystems can develop and support large numbers of species. These reef systems also play a role in shaping future environmental changes. As conditions shift later in the Devonian, reefs will be affected along with the species that depend on them. This connection between environment and ecosystem becomes more important over time. The growth of reefs, combined with increasing biodiversity, marks a significant stage in the development of marine life. These systems demonstrate how structure, stability, and interaction can support complex ecosystems. The Devonian seas continue to evolve, building toward further changes that will affect both ocean and land. During the Devonian, The arrangement of continents is very different from the world today, and these positions influence both ocean movement and climate. Large land masses slowly move toward one another over long periods, changing the shape of coastlines and shallow seas. These gradual shifts affect how water circulates and how marine environments develop. One of the major land masses forming during this time is Euramerica, created as smaller continents come together. This process changes the distribution of shallow marine environments by creating new coastlines and enclosed seas. These areas become important regions for marine life to expand and interact. To the south, Gondwana remains a massive and stable landmass that influences global climate patterns. Its size affects wind systems, ocean currents, and temperature distribution across the planet. These factors contribute to the overall stability of Devonian conditions, especially in marine environments. Sea levels remain relatively high for much of the Devonian, allowing water to cover large portions of continental areas. This creates widespread shallow seas that support a wide range of marine ecosystems. These environments provide space for organisms to grow, reproduce, and interact. The connection between continents and oceans becomes more important as these systems develop. Changes in land position influence water flow, which in turn affects nutrient distribution and temperature. These changes impact where different species are able to survive. In shallow seas, sunlight continues to reach the bottom, supporting reef growth and the expansion of marine life. These conditions allow ecosystems to remain productive and stable over long periods. Stability at this level supports increasing complexity within the ocean. At the same time, the movement of continents begins to create barriers and pathways within the ocean. Some regions become more isolated, while others become more connected. These differences influence how species spread and how populations develop. Isolated regions may develop unique species that are adapted to specific conditions. In contrast, connected regions allow species to move more freely and interact with a wider range of organisms. This creates variation in biodiversity across different parts of the ocean. Ocean currents play a key role in distributing heat and nutrients throughout the marine environment. These currents are influenced by the shape and position of continents, as well as by wind patterns. The movement of water helps maintain stable conditions that support life. As continents continue to shift, these currents may change direction or strength, altering environmental conditions in different regions. These changes can affect the availability of food and the distribution of species. Organisms must adapt to these shifting conditions to survive. The climate during the early Devonian remains generally warm and stable, supporting widespread marine ecosystems. This stability allows life to expand without frequent disruptions. Over time, however, gradual changes begin to influence both ocean and land environments. The interaction between land and ocean becomes more complex as plant life begins to develop on land. Although still limited, these early plants start to influence soil formation and nutrient flow. This connection between land and water will become more important as plant life expands. Rivers begin to carry sediments and nutrients from land into the ocean, affecting marine environments. These inputs can support plankton growth and influence the structure of food webs. Changes in nutrient levels can have widespread effects across the ecosystem. In some areas, Enclosed seas may experience different conditions than open ocean environments. These regions can develop unique temperature or oxygen levels, affecting the types of organisms that can survive there. This creates additional variation within the marine system. The combination of high sea levels, shifting continents, and stable climate conditions creates a dynamic but supportive environment for life. Organisms continue to diversify and adapt within these changing conditions. The Devonian Ocean remains a place of constant interaction and growth. As the period continues, the gradual movement of land masses begins to set the stage for future environmental changes. These changes will influence both marine and terrestrial ecosystems. The connections established during this time will continue to shape life in later periods. The distribution of shallow seas remains one of the most important factors in supporting marine life. These environments provide access to sunlight, nutrients, and space for growth. As long as these conditions remain stable, ecosystems are able to expand. The interaction between different regions of the ocean creates a network of connected systems. Species move between areas, linking ecosystems together through migration and feeding. This movement helps maintain balance across the larger marine environment. Despite the overall stability, small changes continue to influence how ecosystems develop. Variations in temperature, nutrient levels, and water movement create differences between regions. These differences drive adaptation and specialization among species. The Devonian world is shaped not only by the organisms within it, but also by the physical arrangement of land and sea. These large-scale features influence every aspect of the environment. Understanding these connections helps explain how life is able to expand and change. As continents continue to shift and oceans continue to circulate, the conditions that support life remain in place. This allows the processes of evolution and adaptation to continue without interruption. The Devonian remains a period of growth, complexity, and gradual change. As the Devonian continues, life on land begins to change in ways that will affect the entire planet. Early plants, which were once small and limited in size, start to grow taller and develop stronger structures. These changes allow them to spread across larger areas and form the first true forests. These early forests are made up of plants that develop woody trunks, allowing them to support their own weight as they grow upward. This vertical growth allows them to reach more sunlight, which is necessary for producing energy. As more plants compete for light, height becomes an advantage. One of the most important plants during this time is Archaeopteris, a tree-like organism that shows features similar to both modern trees and earlier plant forms. It has a strong trunk, branching structure, and leaves that allow it to capture sunlight efficiently. This makes it one of the dominant plants in Devonian forests. The development of roots plays a major role in how these plants interact with the land. Roots begin to grow deeper into the soil than ever before, reaching into layers that were previously untouched. This allows plants to access water and nutrients more effectively. Deep roots also help stabilize the soil, reducing erosion and holding the ground in place. Before this, much of the land surface is loose and easily moved by water or wind. With the presence of roots, the landscape becomes more stable and structured. As roots break into rock and soil, they contribute to the process of weathering, which breaks down larger materials into smaller particles. This leads to the formation of more developed soils that can support additional plant life. Soil formation becomes faster and more widespread during this period. The spread of plants across the land begins to change the composition of the atmosphere. As plants carry out photosynthesis, they release oxygen and absorb carbon dioxide. This process gradually increases oxygen levels while reducing carbon dioxide in the atmosphere. Changes in atmospheric composition influence both climate and the availability of resources for living organisms. Increased oxygen supports more complex forms of life, while reduced carbon dioxide can affect temperature and weather patterns. These changes are part of a larger system that connects land, water, and air. The presence of forests also changes how water moves across the land. Roots hold soil in place and slow the flow of water, causing rivers to develop more defined paths. Instead of flowing straight and fast, rivers begin to bend and form curves as they move through the landscape. These changes in river behavior create new environments along their edges, including areas with standing water and rich soil. These environments support a wide range of organisms and become important habitats for both plants and animals. The interaction between water and land becomes more complex. Spore-producing plants remain common during much of the Devonian, releasing spores into the air to reproduce. These spores spread across the landscape, allowing plants to colonize new areas. This method of reproduction supports the rapid expansion of plant life. Toward the later part of the Devonian, the first seed plants begin to appear, introducing a new method of reproduction. Seeds provide protection and stored nutrients for developing plants, increasing their chances of survival. This innovation allows plants to spread into more varied environments. As plant life becomes more widespread, it creates new habitats for other organisms. Insects begin to diversify alongside plants, taking advantage of new food sources and shelter. These early insects are small, but they play an important role in the developing ecosystem. Arthropods, including early insects and other related organisms, move across the forest floor and interact with plant material. Some feed on decaying matter, helping to break it down and recycle nutrients into the soil. Others become predators, feeding on smaller organisms. Millipede-like creatures are among the organisms that inhabit these early forests, feeding on plant material and contributing to the breakdown of organic matter. Their presence helps maintain the balance of the ecosystem by returning nutrients to the soil. This process supports continued plant growth. Scorpions are among the first predators on land, using their ability to capture and consume smaller organisms. Their presence introduces a new level of interaction within terrestrial environments. Predation becomes an important factor in shaping land ecosystems. The development of plant life also influences conditions in nearby aquatic environments. As roots break down rock and soil, nutrients are carried by rivers into lakes and oceans. These nutrients can support plankton growth and affect marine food webs. Increased nutrient flow can lead to changes in water conditions, including the availability of oxygen. In some cases, this may contribute to environments where oxygen levels are lower than normal. These changes can have significant effects on marine organisms. The connection between land and ocean becomes more pronounced as plants continue to spread. What happens on land begins to influence what happens in the water. This interaction creates a more integrated system that links different environments together. Forests provide shade and moisture, creating conditions that allow more organisms to survive on land. These environments offer protection from direct sunlight and help maintain stable temperatures. This makes them suitable habitats for a growing variety of life forms. As these ecosystems develop, interactions between species become more complex. Organisms compete for resources, respond to predators, and adapt to changing conditions. Each of these interactions contributes to the overall structure of the environment. The Devonian marks a turning point in the history of life on land, as plants transform the landscape and create new opportunities for other organisms. These changes set the stage for further development in later periods. The expansion of plant life is one of the most important developments of this time. The effects of these changes extend beyond individual ecosystems, influencing global processes such as climate and atmospheric composition. The growth of forests plays a role in shaping conditions that will affect life for millions of years. These long-term impacts continue to influence the direction of evolution. As the Devonian progresses, the transformation of the land becomes more visible, with forests covering larger areas and supporting more life. The connection between plants, soil, and atmosphere continues to strengthen. These developments represent a major step in the expansion of life beyond the ocean. The changes taking place on land are not separate from those in the ocean, but are part of a larger system that connects all environments. As plants alter the landscape, they also influence the conditions in nearby waters. This connection will play a role in future events that affect both land and sea. As the Devonian continues, the spread of plant life across the land begins to influence the planet in ways that extend far beyond the forests themselves. What was once mostly bare rock and thin soil becomes increasingly covered by vegetation that changes how the surface of the earth behaves. These changes affect not only land environments, but also the oceans that surround them. The growth of forests increases the amount of organic material produced on land, including leaves, stems, and roots. When this material breaks down, it becomes part of the soil, adding nutrients and changing its composition. Over time, soils become deeper and more capable of supporting large and complex plant communities. As plant material accumulates, microorganisms begin to play a larger role in breaking it down and recycling nutrients. Bacteria and fungi contribute to this process by decomposing organic matter and returning essential elements to the soil. This interaction supports continued plant growth and helps maintain the balance of terrestrial ecosystems. The presence of roots continues to reshape the landscape by breaking apart rock and stabilizing soil. This process increases the rate at which minerals are released into the environment. These minerals are then carried by water into rivers and eventually into the ocean, linking land and marine systems. As rivers carry more nutrients into the ocean, they support increased plankton growth in coastal and shallow marine environments. This leads to higher productivity in these areas, allowing populations of marine organisms to expand. The increased availability of food affects the structure of marine ecosystems. However, this increase in nutrients can also lead to changes in oxygen levels within the water. When plankton populations grow rapidly and then die, their decomposition consumes oxygen. In some areas, this process can reduce oxygen levels enough to create difficult conditions for marine life. These low oxygen environments, sometimes referred to as anoxic conditions, can limit which organisms are able to survive. Species that depend on higher oxygen levels may decline, while others that tolerate lower oxygen conditions may persist. This creates shifts in the composition of marine communities. The connection between land-based plant growth and ocean conditions becomes more evident as these processes continue. What happens on land is no longer isolated, but directly affects marine ecosystems. This relationship adds another layer of complexity to the Devonian world. At the same time, atmospheric changes continue as plants absorb carbon dioxide and release oxygen. This gradual shift alters the balance of gases in the atmosphere, influencing global climate patterns. Lower carbon dioxide levels may contribute to cooling trends over long periods. Changes in temperature can affect ocean circulation and the distribution of species. Cooler conditions may alter where certain organisms are able to survive, leading to shifts in biodiversity. These changes can occur slowly, but their effects can be widespread. The expansion of forests also influences how water is retained and released on land. Vegetation slows the movement of water, allowing more of it to be absorbed into the ground. This leads to more stable water systems and reduces sudden changes in flow. As water systems become more stable, environments along rivers and lakes become more predictable. These areas support a variety of organisms that depend on consistent conditions. Stability in these habitats allows ecosystems to develop further. In these environments, early terrestrial ecosystems continue to expand and diversify. Arthropods move through the leaf litter and soil, interacting with plant material and other organisms. Their presence contributes to the breakdown of organic matter and the recycling of nutrients. Some arthropods begin to develop more advanced structures for movement and feeding. These changes allow them to exploit different parts of the environment and reduce competition with other species. This diversification increases the complexity of land-based ecosystems. The interaction between plants and arthropods creates new ecological relationships, including herbivory and predation. Some organisms feed directly on plant material, while others feed on those that do. These relationships form the basis of food webs on land. As these food webs develop, energy begins to flow through terrestrial ecosystems in ways similar to those in the ocean. Each level of the system depends on the one below it, creating interconnected networks. These networks become more stable as they grow in complexity. The spread of plant life also creates microenvironments with varying conditions of light, moisture, and temperature. These variations allow different species to occupy specific niches within the same general area. This leads to increased biodiversity within terrestrial ecosystems. In some regions, dense plant growth may reduce light reaching the ground, creating shaded environments. These areas support organisms that are adapted to lower light conditions. Other areas remain more open, supporting species that require more sunlight. The diversity of habitats created by plants allows for a greater number of species to coexist. This reduces direct competition and encourages specialization among organisms. Specialization becomes an important factor in the continued expansion of life on land. As terrestrial ecosystems grow, they begin to influence the broader environment in more noticeable ways. The exchange of gases between plants and the atmosphere continues to shape global conditions. These changes affect both land and marine systems. At the same time, marine ecosystems continue to respond to changes in nutrient input and oxygen levels. Some regions may experience stress as conditions shift, leading to changes in species composition. These responses highlight the interconnected nature of the Devonian world. The combination of plant expansion, nutrient flow, and atmospheric change creates a system where land and ocean are closely linked. Each system influences the other, creating feedback loops that drive further change. These processes operate over long periods, gradually shaping the environment. Toward the later part of the Devonian, these combined effects begin to contribute to larger-scale environmental changes. Fluctuations in oxygen levels and nutrient distribution can create challenges for marine life. These challenges may play a role in events that will occur later in the period. The Devonian is not only a time of growth and expansion, but also a time when the balance of systems becomes more delicate. As complexity increases, so does the potential for disruption. Small changes can have larger effects across interconnected systems. Despite these challenges, life continues to adapt and respond to changing conditions. Organisms that can adjust to new environments survive and continue to evolve. This ongoing process drives the continued development of both land and marine ecosystems. The changes taking place during this time set the stage for future transitions that will shape the course of life on Earth. The expansion of plant life, the development of complex ecosystems, and the connection between land and ocean all contribute to this transformation. These processes will continue to influence life long after the Devonian comes to an end. As the Devonian progresses, the balance within marine ecosystems begins to show signs of stress as conditions gradually shift. The same systems that supported rapid growth and diversification now become more sensitive to change. Increasing complexity means that disruptions can spread more easily through interconnected food webs. Changes in nutrient flow from land continue to influence coastal and shallow marine environments. As plant life expands, more minerals and organic material are carried into the ocean by rivers. These inputs can support large plankton blooms, but they can also create unstable conditions. When plankton populations increase rapidly, they eventually decline as resources are used up. The decomposition of these large amounts of organic matter consumes oxygen in the water. This process can reduce oxygen levels to the point where many marine organisms struggle to survive. In areas where oxygen becomes limited, conditions shift toward environments that support fewer species. Organisms that require higher oxygen levels begin to decline, while others that tolerate low oxygen conditions may remain. This creates uneven patterns of survival across different regions. These low oxygen zones do not affect all parts of the ocean equally, but their presence disrupts established ecosystems. Species that once thrived in certain areas may be forced to move or face decline. This leads to changes in population distribution and alters the structure of marine communities. At the same time, climate conditions begin to show gradual changes that influence both ocean and land environments. Variations in temperature can affect ocean circulation and the distribution of nutrients. These changes may not be sudden, but their effects accumulate over time. Shifts in ocean circulation can alter the movement of oxygen-rich water into deeper regions. When circulation slows or changes direction, some areas may receive less oxygen. This further contributes to the development of low-oxygen environments. Marine organisms must respond to these changing conditions in different ways, depending on their abilities. Some species are able to move to areas with more favorable conditions, while others remain in place and attempt to adapt. Not all species are able to survive these changes. Large predators and highly specialized organisms are often more vulnerable to environmental shifts. Their reliance on specific prey or conditions makes it harder for them to adjust when those conditions change. This can lead to declines in populations that were previously dominant. Reef systems, which were once centers of biodiversity, begin to experience stress as environmental conditions shift. Changes in water chemistry and oxygen levels can affect the organisms that build and maintain reefs. As these organisms decline, the structure of the reef can begin to break down. The loss of reef structure reduces available habitat for many species that depend on these environments. This leads to further declines in biodiversity as fewer organisms are able to find suitable living conditions. The effects of these changes can spread throughout the ecosystem. Fish populations respond to these shifts in different ways, depending on their adaptability. Some species are able to adjust their feeding strategies or move to new areas. Others may decline if they cannot adapt quickly enough to changing conditions. The complexity of the food web means that changes at one level can affect many others. A decline in plankton or reef-building organisms can influence fish populations, which in turn affects predators. This chain of effects can lead to widespread changes within the ecosystem. On land, plant life continues to influence conditions through its impact on soil and atmosphere. The expansion of forests continues to alter nutrient flow and atmospheric composition. These changes remain connected to what is happening in marine environments. The interaction between land and ocean becomes increasingly important as both systems respond to changing conditions. Nutrient input, atmospheric changes, and water flow all contribute to the overall state of the environment. These connections create a complex system where multiple factors influence outcomes. As environmental stress increases, ecosystems may reach points where they can no longer maintain previous levels of stability. When this happens, rapid changes in species composition can occur. These shifts may not be uniform, but they can have significant impacts. Some regions may experience more severe changes than others, depending on local conditions and environmental factors. This creates a patchwork of ecosystems that are affected in different ways. The overall pattern becomes more varied and less predictable. The Devonian period includes several extinction events that are linked to these environmental changes. These events occur over extended periods rather than as a single sudden occurrence. Their effects are seen in the loss of certain groups and changes in ecosystem structure. The late Devonian extinction is one of the most significant events during this time. It affects many marine species, particularly those associated with reef systems. The causes of this event are complex and involve multiple interacting factors. Possible contributing factors include changes in climate, ocean chemistry, and oxygen levels. These factors do not act alone, but combine to create conditions that are difficult for many organisms to survive. The result is a reduction in biodiversity and a restructuring of ecosystems. Despite these challenges, Not all species are affected equally, and some are able to survive and adapt. These surviving organisms become the foundation for future ecosystems. Their ability to persist through changing conditions allows life to continue. The Devonian demonstrates how interconnected systems can both support and challenge life. Growth and complexity bring new opportunities, but also increase vulnerability to change. The same processes that drive expansion can also contribute to disruption. As the period continues, the effects of environmental stress become more apparent, leading to lasting changes in marine ecosystems. The balance that once supported widespread growth is altered, and new conditions begin to shape the future of life. As the late Devonian extinction unfolds, the effects on marine ecosystems become more visible across different regions of the ocean. The gradual loss of species changes the structure of food webs and alters how energy moves through the system. What was once a highly diverse environment begins to shift towards simpler and more uneven conditions. Reef systems, which had supported large numbers of organisms, are among the most affected environments. Many of the organisms that build and maintain these reefs begin to decline under changing conditions. As reef structures weaken, they provide less shelter and fewer resources for other species. The reduction of reef habitats leads to a decline in biodiversity, as many organisms depend on these environments for survival. Species that cannot adapt to new conditions or move to other habitats begin to disappear. This loss affects not only individual species, but also the relationships between them. As reef systems break down, open water environments become more dominant in some regions. Organisms that are better suited to open conditions may expand into these areas. This shift changes the balance between different types of habitats within the ocean. Oxygen levels continue to play a major role in shaping these changes, as low oxygen conditions limit the survival of many species. In areas where oxygen is reduced, only certain organisms are able to persist. These conditions create environments that support fewer species and simpler food webs. The decline of oxygen in some regions may be linked to increased nutrient input from land and changes in ocean circulation. When nutrients lead to large plankton blooms, the subsequent decomposition consumes oxygen. This process can create conditions that are difficult for many marine organisms. As these low oxygen zones expand or shift, organisms must respond by moving or adapting. Some species migrate to areas with more favorable conditions, while others are unable to adjust and decline. This movement alters the distribution of species across the ocean. Large predators that depend on stable populations of prey may also be affected by these changes. As prey becomes less available or more unevenly distributed, predators must adapt their behavior or face decline. This can lead to a reduction in the number of large predators in some regions. At the same time, smaller and more adaptable species may become more common in areas where conditions are unstable. These organisms are often better able to survive changes in oxygen levels and resource availability. Their success contributes to the restructuring of marine ecosystems. The extinction events of the late Devonian do not occur all at once, but rather over extended periods with multiple phases. Each phase contributes to the gradual loss of species and changes in ecosystem structure. This prolonged process allows for both decline and adaptation to occur simultaneously. Some groups of organisms are more heavily affected than others, particularly those with specialized roles or narrow environmental requirements. Species that rely on specific conditions are less able to adjust to changes. In contrast, more generalist species may be better able to survive. The decline of certain groups opens ecological space that can be filled by other organisms. Surviving species may expand into areas that were previously occupied by others. This process leads to new patterns of distribution and interaction within the ecosystem. On land, plant life continues to influence conditions through its effects on soil, atmosphere, and water systems. The continued expansion of forests contributes to ongoing changes in nutrient flow and atmospheric composition. These processes remain connected to changes in the ocean. The interaction between terrestrial and marine systems continues to shape the overall environment during this time. Changes in one system can influence the other, creating feedback loops that drive further change. This interconnectedness becomes a defining feature of the Devonian world. Climate variations may also contribute to environmental stress during the late Devonian. Changes in temperature can affect ocean circulation, nutrient distribution, and the availability of oxygen. These factors combine to create conditions that are difficult for many species to tolerate. As ecosystems respond to these pressures, the structure of marine communities becomes less complex in some regions. Fewer species occupy each level of the food web, and interactions between species become less varied. This simplification can reduce the stability of the ecosystem. Despite these challenges, life does not disappear, but continues to adapt and reorganize under new conditions. Species that survive the extinction events form the basis of future ecosystems. Their adaptations allow them to persist and eventually diversify again. The late Devonian extinction represents a major turning point in the history of life, marking the end of one phase of development and the beginning of another. The loss of certain groups changes the direction of evolution. New opportunities arise for the organisms that remain. As the Devonian period comes to a close, the combined effects of environmental change and extinction reshape both marine and terrestrial ecosystems. The systems that once supported rapid expansion are replaced by new conditions that favor different types of organisms. This transition sets the stage for the next period in Earth's history. The Devonian demonstrates how growth and complexity can lead to both expansion and vulnerability within ecosystems. The same processes that support diversification can also contribute to instability when conditions change. This balance between growth and disruption continues to shape life on Earth. As the period ends, the changes that have taken place leave lasting impacts on the structure of ecosystems and the direction of evolution. The Devonian world is no longer the same as it was at its beginning. The foundation has been set for new developments that will continue in the periods that follow. As the Devonian period draws toward its final stages, the effects of environmental change and extinction begin to reshape ecosystems in lasting ways. The loss of certain species creates gaps within food webs, altering how energy moves through marine and terrestrial systems. These changes do not stop the development of life, but redirect it into new pathways. Marine ecosystems that were once dominated by reef systems and highly specialized organisms begin to shift toward more flexible and adaptable structures. With the decline of many reef-building species, open water environments become more important in supporting life. Organisms that can survive in a wider range of conditions begin to play a larger role. Fish that are less specialized in their feeding and habitat requirements are more likely to persist through changing conditions. These species are able to adjust their behavior, diet, or location in response to environmental shifts. This flexibility becomes a key factor in survival during periods of instability. At the same time, some groups that were previously less dominant begin to expand into ecological spaces left open by declining species. This expansion allows new interactions to develop and changes the overall structure of the ecosystem. The balance of life continues to adjust as conditions evolve. Cartilaginous fish, including early sharks, continue to diversify and spread across marine environments. Their efficient movement and adaptable feeding strategies allow them to occupy a variety of roles. These characteristics help them persist through environmental changes that affect other groups more strongly. Bony fish also continue to play an important role in marine ecosystems, maintaining a wide range of forms and behaviors. Their ability to adapt to different conditions allows them to survive in both stable and changing environments. This adaptability contributes to their long-term success. The decline of placoderms, including large armored fish, marks a significant change in marine predator dynamics. These heavily armored species are less able to adapt to changing conditions and begin to disappear. Their decline opens opportunities for other predators to expand. As predator populations shift, prey species must also adjust to new threats and changing conditions. Some species develop new strategies for avoiding predation, while others rely on existing adaptations. These interactions continue to drive evolutionary change. On land, plant life continues to expand and influence environmental conditions in ways that extend beyond individual ecosystems. Forests cover larger areas, creating stable habitats that support a growing variety of organisms. These environments become increasingly important in shaping the future of terrestrial life. The continued development of soils allows plants to grow more effectively and supports the expansion of ecosystems. Deeper and more nutrient-rich soils provide a foundation for larger and more complex plant communities. This process continues to transform the landscape. Arthropods remain a dominant group on land, interacting with plant life and contributing to the cycling of nutrients. Their presence supports the breakdown of organic material and the maintenance of soil health. These interactions are essential for the stability of terrestrial ecosystems. As terrestrial ecosystems grow more complex, the connections between land and water become even more significant. Nutrient flow, atmospheric changes, and water movement link these environments together. Changes in one system can influence the other in multiple ways. The late Devonian extinction events reduce biodiversity, but they also create conditions for new forms of life to develop. The removal of certain species allows others to expand and adapt to new roles. This process leads to the reorganization of ecosystems. In marine environments, food webs become less complex in some regions, but remain dynamic and responsive to change. Surviving species continue to interact and adapt, maintaining the flow of energy through the system. Over time, complexity begins to increase again. The recovery from extinction is not immediate, but occurs gradually as ecosystems stabilize under new conditions. Species that are able to survive the initial changes begin to diversify and fill available ecological niches. This process sets the stage for future evolutionary developments. Environmental conditions during this time continue to fluctuate, influencing how ecosystems develop. Variations in temperature, oxygen levels, and nutrient availability create ongoing challenges for organisms. These conditions require continued adaptation and flexibility. As the Devonian transitions into the next period, the foundations of modern ecosystems begin to take shape. Many of the structures and interactions that define later ecosystems have their origins in this time. The changes that occur during the Devonian have lasting effects. The movement of life onto land continues to progress, supported by the development of plants and early tetrapods. These organisms begin to explore new environments and establish new ecological relationships. The transition to land becomes an increasingly important aspect of life on Earth. Marine ecosystems also continue to evolve, with surviving groups adapting to changing conditions and expanding into new roles. The decline of some groups allows others to become more prominent. This shift contributes to the ongoing development of marine life. The Devonian period demonstrates how ecosystems can change in response to both internal and external pressures. Growth, competition, and environmental change all contribute to the direction of evolution. These processes are interconnected and influence one another. As the period comes to an end, the combined effects of extinction and adaptation create a new starting point for future development. The systems that emerge are shaped by both what was lost and what survived. This balance defines the transition into the next phase of Earth's history. The legacy of the Devonian is seen in the continued evolution of both marine and terrestrial life. The innovations that occur during this time, including the development of jaws, limbs, and complex ecosystems, continue to influence life long after the period ends. These developments form the foundation for future change. The Devonian does not end with a complete loss of life, but with a transformation that redirects the course of evolution. The processes that drive this transformation continue to operate in later periods. Life moves forward, shaped by the conditions and changes that defined this time. As ecosystems stabilize and begin to recover, the patterns established during the Devonian continue to influence the structure of life. Adaptation, interaction, and environmental connection remain central to survival. These principles will continue to guide the development of life in the periods that follow. As the Devonian comes to an end, the conditions that shaped life during this period begin to give way to new patterns that will define the next stage of Earth's history. The combined effects of environmental change, extinction, and adaptation leave ecosystems altered but still active. Life does not pause, but continues to adjust within the new conditions that have formed. Marine ecosystems that were once highly complex begin to reorganize as surviving species take on new roles. The loss of many reef-building organisms reduces the number of structured habitats available, changing where organisms can live and feed. Open water environments become more important in supporting remaining marine life. In these open environments, species that are able to move efficiently and adapt to changing conditions become more successful. Fish that rely on flexible feeding strategies and broad habitat ranges are more likely to persist. This shift favors organisms that can respond quickly to changes in their surroundings. Cartilaginous fish continue to expand and diversify taking advantage of the changes in marine ecosystems. Their bodies allow for efficient movement, and their sensory systems help them detect prey in different conditions. These traits support their survival in environments where other groups decline. Bony fish also continue to develop and occupy a wide range of ecological roles. Their ability to adapt to different feeding strategies and environments allows them to remain an important part of marine systems. This flexibility contributes to their continued success after the Devonian. The decline of placoderms removes a group that once dominated many marine environments. Without these heavily armored predators, other species are able to expand into the spaces they leave behind. This change alters the balance of predation within the ecosystem. As predator and prey relationships adjust, food webs begin to stabilize under new conditions. Although less complex in some areas, these systems continue to support a variety of organisms. Over time, interactions between species become more structured again. On land, plant life continues to expand and refine the environments it creates. Forests remain a dominant feature of the landscape, providing shelter, food, and stable conditions for a growing number of organisms. These ecosystems continue to increase in complexity. Soil development continues as organic material accumulates and is broken down by microorganisms. This process creates nutrient-rich environments that support further plant growth. The cycle of growth and decomposition becomes more established and efficient. Arthropods continue to diversify on land, interacting with plant life and contributing to the structure of terrestrial ecosystems. Their roles include feeding on plants, decomposing organic material, and preying on other organisms. These interactions create interconnected food webs. Early tetrapods remain closely tied to water, but their ability to move on land continues to improve. Their limbs provide support and allow them to explore environments beyond shallow water. This movement represents an important step in the expansion of vertebrate life. These early land vertebrates still depend on water for reproduction and protection, limiting how far they can move from aquatic environments. However, their presence on land introduces new interactions and pressures within terrestrial ecosystems. These interactions will influence future development. The connection between land and water remains strong, as processes in one environment continue to affect the other. Nutrient flow, atmospheric changes, and water movement link these systems together. This interconnectedness remains a defining feature of life during this time. Atmospheric conditions continue to shift as plants influence the balance of gases. Increased oxygen levels support more active organisms, while changes in carbon dioxide affect climate. These factors contribute to the conditions that shape ecosystems. Climate patterns begin to transition as the Devonian ends, influencing both marine and terrestrial environments. Variations in temperature and moisture affect where organisms can survive. These changes require continued adaptation across different ecosystems. The end of the Devonian marks not a complete break, but a transition into the next phase of Earth's history. The systems that developed during this period provide a foundation for future ecosystems. The changes that occur now will influence what comes next. The legacy of the Devonian is seen in the structures and relationships that continue beyond its end. The development of jaws, limbs, and complex ecosystems remains important in later periods. These features become central to the continued evolution of life. As ecosystems stabilize under new conditions, surviving species begin to diversify again, filling ecological niches that were left open by extinction. This process leads to new patterns of interaction and growth. Over time, complexity begins to increase once more. This diversification does not happen evenly across all environments, but varies depending on local conditions and available resources. Regions with stable conditions may support faster growth in biodiversity, while others recover more slowly. This uneven pattern creates variation in how ecosystems develop. As species diversify, they begin to fill ecological niches that were left open by the loss of earlier organisms. These niches represent specific roles within the ecosystem, such as feeding on certain types of prey or occupying particular habitats. Filling these roles helps restore balance within the system. Over time, the process of diversification leads to increased interaction between species, including competition and predation. These interactions continue to shape the direction of evolution. Each new adaptation creates pressure for further change in other organisms. Marine life continues to adapt to changing conditions, with species adjusting their behavior and distribution. Open water environments remain important, but new forms of structure may develop over time. These changes contribute to the ongoing evolution of marine ecosystems. On land, the continued expansion of plants and the presence of early animals create environments that support increasing biodiversity. These ecosystems become more stable and interconnected. The foundation for future terrestrial life is now firmly in place. The Devonian period demonstrates how life can respond to both opportunity and challenge. Growth and expansion lead to increased complexity, while environmental changes create pressure and require adaptation. These processes work together to shape the direction of evolution. As the period concludes, the world is different from how it began, with new forms of life and new interactions defining the environment. The changes that occurred during the Devonian continue to influence life in the periods that follow. The transition into the next phase of Earth's history is already underway. As the Devonian transitions fully into the next period, the systems shaped by millions of years of change continue to evolve under new conditions. The loss of some species and the survival of others create a different balance within ecosystems. These changes influence how life will develop moving forward. Marine environments continue to reorganize as species adjust to the absence of groups that once dominated. The decline of reef systems reduces the number of structured habitats, leading to greater reliance on open water environments. Organisms that can survive in these conditions become more common. Fish that are able to move efficiently and adapt to different food sources continue to thrive. Their flexibility allows them to respond to changes in prey availability and environmental conditions. This adaptability becomes an important factor in long-term survival. Cartilaginous fish, including early sharks, expand further into different ecological roles. Their ability to detect movement and navigate efficiently gives them an advantage in varied environments. These traits support their continued presence in marine ecosystems. Bony fish maintain their diversity and continue to occupy a wide range of habitats. Their structural adaptability allows them to use different feeding strategies and movement patterns. This versatility contributes to their ongoing success. The restructuring of marine food webs creates new interactions between species. Predators and prey adjust to new conditions, leading to changes in behavior and distribution. These interactions shape the structure of ecosystems as they stabilize. Some species begin to specialize further, focusing on specific roles within the ecosystem. This specialization can increase efficiency in stable conditions, but may also limit adaptability. The balance between specialization and flexibility becomes important. Open water environments become increasingly important as areas of interaction and movement. Organisms that are suited to these environments rely on sustained swimming and efficient energy use. These conditions favor certain body structures and behaviors. Open water environments require organisms to rely on sustained movement rather than protection from structure. Fish that live in these areas must conserve energy while traveling longer distances in search of food. This leads to body shapes that reduce resistance in the water and allow for more efficient swimming. In these environments, visibility can vary, and organisms must rely on both sight and other sensory systems to detect movement. Subtle changes in pressure or vibration can signal the presence of prey or predators. These signals allow organisms to respond before direct contact occurs. The lack of physical shelter in open water means that behavior becomes an important factor in survival. Some species move in coordinated groups to reduce individual risk, while others rely on speed or sudden changes in direction. These strategies help organisms avoid being captured in environments where hiding is limited. At the same time, new forms of structure may begin to develop in marine environments, although not at the same scale as earlier reefs. These structures provide habitats for organisms that depend on shelter and localized resources. They contribute to the gradual rebuilding of ecosystem complexity. On land, plant life continues to expand and influence environmental conditions. Forests cover larger areas and create stable habitats for a variety of organisms. These environments support increasing biodiversity and more complex interactions. Soil systems become more developed as organic material accumulates and is processed by microorganisms. This leads to nutrient-rich conditions that support continued plant growth. The interaction between plants and soil becomes more efficient over time. Arthropods continue to diversify and occupy different roles within terrestrial ecosystems. Some feed on plants, while others act as predators or decomposers. These roles contribute to the structure and stability of land-based food webs. Early tetrapods continue to explore terrestrial environments, although they remain closely connected to water. Their limbs allow them to move across land, but their dependence on aquatic conditions limits their range. These organisms represent an important stage in the transition of vertebrate life. As terrestrial ecosystems become more complex, interactions between species increase. Competition for resources, predation, and environmental pressures shape how organisms adapt. These processes contribute to the continued development of life on land. The connection between land and marine environments remains strong, as processes in one system affect the other. Nutrient flow, atmospheric changes, and water movement link these environments together. This interconnectedness continues to influence the structure of ecosystems. Atmospheric conditions continue to evolve as plants influence the balance of gases. Increased oxygen levels support more active organisms, while changes in carbon dioxide affect climate patterns. These factors contribute to environmental conditions across the planet. Climate conditions continue to shift gradually, affecting both marine and terrestrial ecosystems. Variations in temperature and moisture influence where species can survive and how they interact. These changes require ongoing adaptation. As ecosystems stabilize after the changes of the Devonian, surviving species begin to diversify again. This process leads to the development of new forms and interactions. Over time, complexity begins to increase once more. Marine ecosystems continue to adapt to changing conditions, with species adjusting their behavior and distribution. Open water environments remain central to these systems, while new structures may develop gradually. These changes contribute to the ongoing evolution of marine life. On land, the expansion of plant life and the presence of early animals create conditions that support further diversification. These ecosystems become more stable and interconnected. The foundation for future terrestrial life continues to strengthen. The transition from the Devonian into the next period demonstrates how life responds to both disruption and opportunity. The loss of certain groups creates space for others to expand and adapt. This process drives the continued development of ecosystems. The patterns established during the Devonian, including adaptation, interaction, and environmental connection, continue to influence life moving forward. These patterns shape how organisms respond to changing conditions. They remain central to the process of evolution. As the world moves beyond the Devonian, the systems that developed during this period continue to evolve under new conditions. Life remains dynamic and responsive, shaped by both past changes and present environments. The foundations established during this time will support future developments in the history of life. As the period following the Devonian begins, ecosystems continue to reorganize under conditions shaped by both loss and survival. The changes that occurred during the late Devonian extinction leave behind environments that are less crowded but still active. These environments provide opportunities for species that can adapt to new conditions. Marine ecosystems continue to shift towards structures that rely less on large reef systems and more on open water interactions. Without the same level of reef complexity, organisms must depend more on movement and flexibility to survive. This leads to a greater emphasis on efficient swimming and adaptable feeding strategies. Fish that can travel long distances and adjust to changing food sources become more successful in these environments. Their ability to move between different areas allows them to find resources even when conditions are uneven. This mobility becomes a key factor in survival. Cartilaginous fish continue to expand into new ecological roles, taking advantage of the changes in marine environments. Their lightweight skeletal structure supports efficient movement, allowing them to conserve energy while remaining active hunters. These traits make them well suited to open water conditions. Bony fish also remain highly adaptable, with many species continuing to diversify into different forms. Their structural flexibility allows them to develop a wide range of feeding strategies. This diversity supports their continued presence in many types of marine habitats. As food webs reorganize, interactions between species begin to stabilize under new conditions. Predators adjust to changes in prey availability, while prey species adapt to new threats. These adjustments help restore balance within ecosystems. The reduction in biodiversity during the late Devonian creates open ecological niches that can be filled by surviving species. These niches represent opportunities for organisms to expand into new roles. Over time, this process contributes to the recovery of ecosystem complexity. Some species begin to specialize in ways that allow them to use resources more efficiently. This specialization can provide advantages in stable conditions, but may limit flexibility if conditions change again. The balance between specialization and adaptability continues to influence survival. Open water environments remain central to marine ecosystems, requiring organisms to rely on behavior and movement rather than physical shelter. Fish that inhabit these areas often develop streamlined bodies that reduce resistance in the water. This allows them to travel efficiently over long distances. In these environments, sensory systems become increasingly important for detecting movement and changes in surroundings. Organisms rely on subtle cues, such as vibrations and pressure changes, to locate prey or avoid predators. These abilities improve survival in areas where visibility may be limited. Group behavior continues to play a role in survival for many species, especially smaller fish that rely on coordinated movement. By moving together, individuals reduce the likelihood of being targeted by predators. This strategy remains effective in environments where hiding is not possible. On land, plant life continues to shape the environment by stabilizing soil and influencing water flow. Forests provide consistent habitats that support a growing variety of organisms. These environments remain important for the continued development of terrestrial ecosystems. Soil systems become more complex as organic material accumulates and is processed by microorganisms. This process creates conditions that support larger and more diverse plant communities. The interaction between plants and soil continues to strengthen. Arthropods continue to expand their roles within terrestrial ecosystems, contributing to decomposition, predation, and herbivory. These interactions create food webs that link different levels of the ecosystem. As these systems grow, they become more stable and interconnected. Early tetrapods continue to develop their ability to move on land, although they remain closely tied to water. Their limbs provide support and allow them to navigate uneven surfaces. These adaptations represent an important stage in the expansion of vertebrate life. As terrestrial ecosystems become more established, interactions between species increase in complexity. Competition for resources, predator-prey relationships, and environmental pressures all contribute to how organisms evolve. These interactions shape the structure of ecosystems over time. The connection between land and marine environments remains strong, as processes in one system continue to affect the other. Nutrient flow from land influences marine productivity, while atmospheric changes affect both environments. This interconnectedness continues to shape the global system. Atmospheric conditions continue to evolve as plant life influences the balance of gases. Increased oxygen levels support more active organisms, while changes in carbon dioxide influence climate patterns. These factors contribute to environmental conditions that affect all forms of life. Climate patterns continue to shift gradually, influencing temperature, moisture, and the distribution of species. Organisms must adapt to these changes to survive. These shifts contribute to ongoing evolution within ecosystems. As ecosystems recover from earlier disruptions, complexity begins to increase again, though not immediately to previous levels. surviving species expand into available niches and begin to diversify. This process supports the gradual rebuilding of ecosystem structure. Marine environments continue to evolve as species adapt to changing conditions and expand into new roles. Open water remains a central feature, but localized structures may begin to develop over time. These changes contribute to the continued evolution of marine life. On land, the continued expansion of plant life and the presence of early animals create conditions that support further diversification. These ecosystems become more stable and interconnected. The foundation for future terrestrial life continues to strengthen. The period following the Devonian demonstrates how ecosystems can recover and reorganize after significant change. The loss of certain species creates opportunities for others to expand and adapt. This process drives the continued development of life. The patterns established during the Devonian, including adaptation, interaction, and environmental connection, continue to influence life moving forward. These patterns shape how organisms respond to changing conditions. They remain central to the process of evolution. As life continues to evolve, the systems that developed during the Devonian provide a framework for future change. The innovations and interactions that began during this time continue to influence the direction of evolution. These processes ensure that life remains dynamic and responsive. The transition beyond the Devonian marks not an end, but a continuation of development under new conditions. Life continues to adapt, expand, and interact within a changing environment. The legacy of the Devonian remains present in the systems that follow. As ecosystems continue to stabilize after the changes at the end of the Devonian, patterns of interaction between species begin to form more consistent structures. These patterns are based on feeding relationships, movement, and environmental conditions that shape how organisms survive. Over time, these interactions create systems that are both stable and capable of further change. Marine food webs begin to reorganize around species that are able to adapt to a wider range of conditions. Organisms that rely on specific environments or narrow food sources are less common than those that can adjust their behavior. This shift leads to ecosystems that are more flexible and better able to respond to change. In open water environments, fish that can travel long distances and conserve energy continue to play a central role. Their ability to move between different regions allows them to take advantage of available resources. This mobility supports the stability of food webs across large areas. Cartilaginous fish continue to expand their presence, using efficient movement and sensory awareness to locate prey. Their ability to detect subtle changes in the water allows them to respond quickly to opportunities and threats. These traits make them effective predators in a variety of conditions. Bony fish maintain their diversity and continue to occupy a wide range of ecological roles. Their structural adaptability allows them to develop feeding strategies suited to different environments. This flexibility supports their continued success in both stable and changing systems. As predator-prey relationships stabilize, organisms begin to develop more predictable behaviors based on their roles within the ecosystem. These behaviors include feeding patterns, movement strategies, and responses to environmental conditions. Predictability contributes to the stability of the system. Some species continue to specialize in ways that allow them to use resources more efficiently. This specialization can increase success in stable environments, but may reduce flexibility if conditions change. The balance between specialization and adaptability remains important. Open water environments require organisms to rely on movement and awareness rather than physical protection. Fish in these environments often develop streamlined bodies that reduce resistance in the water. This allows them to travel efficiently while conserving energy. In these areas, sensory systems play an important role in detecting movement and changes in the environment. Organisms rely on signals such as vibrations and pressure differences to locate prey or avoid predators. These abilities are essential in environments where visibility may be limited. Group behavior continues to provide advantages for smaller fish, allowing them to reduce individual risk through coordinated movement. By moving together, they make it more difficult for predators to target a single individual. This strategy remains effective in open water conditions. On land, plant life continues to shape ecosystems by providing structure, food, and stable conditions for other organisms. Forests support a variety of species that interact in complex ways. These interactions contribute to the development of stable terrestrial ecosystems. Soil systems continue to develop as organic material is broken down and recycled by microorganisms. This process supports plant growth and contributes to the stability of ecosystems. The interaction between plants, soil, and microorganisms remains essential. Arthropods continue to diversify and occupy a wide range of roles within terrestrial ecosystems. Some feed on plants, while others act as predators or decomposers. These roles contribute to the structure and function of food webs on land. Early tetrapods continue to explore terrestrial environments, although they remain closely connected to water. Their limbs allow them to move across land, but their dependence on aquatic conditions limits their range. These organisms represent an important stage in the development of vertebrate life on land. As terrestrial ecosystems become more complex, interactions between species increase in both number and variety. Competition for resources, predation, and environmental pressures shape how organisms adapt. These processes contribute to the continued development of ecosystems. The connection between land and marine environments remains strong, as processes in one system continue to influence the other. Nutrient flow from land affects marine productivity, while atmospheric changes impact both environments. This interconnectedness remains a defining feature. Atmospheric conditions continue to evolve as plant life influences the balance of gases. Increased oxygen supports more active organisms, while changes in carbon dioxide affect climate patterns. These changes influence the conditions under which life develops. Climate patterns continue to shift gradually, affecting temperature, moisture, and the distribution of species. Organisms must respond to these changes to survive. Adaptation remains a key factor in long-term success. As ecosystems stabilize, the interactions between species become more organized and structured. This organization supports the flow of energy through food webs and contributes to overall stability. Stable systems are better able to support a variety of life. Marine ecosystems continue to evolve as species adapt to changing conditions and expand into new roles. Open water remains a central feature, but localized structures may begin to develop over time. These changes contribute to ongoing development. On land, the expansion of plant life and the presence of early animals create conditions that support increasing biodiversity. These ecosystems become more stable and interconnected. The foundation for future terrestrial life continues to strengthen. The processes of adaptation, interaction, and environmental connection that developed during the Devonian continue to shape life beyond that period. These processes remain central to the evolution of ecosystems. They guide how organisms respond to changing conditions. As life continues to evolve, the systems that emerged from the Devonian provide a framework for future development. The interactions and structures that form during this time influence later ecosystems. These connections ensure continuity in the history of life. The stabilization of ecosystems following periods of change demonstrates the ability of life to adjust and persist. Even after disruption, organisms find ways to survive and adapt. This resilience is a defining feature of life on Earth. The legacy of the Devonian is seen in the continued development of complex ecosystems and the expansion of life into new environments. The patterns established during this time continue to influence the direction of evolution. Life remains dynamic and responsive as it moves forward. As the transition beyond the Devonian continues, one of the most important developments becomes clearer in the structure of vertebrate life. The early tetrapods that first appeared during the Devonian begin to diversify and refine their ability to live on land. These organisms still depend on water, but their movement and behavior begin to show greater independence from aquatic environments. The limbs that developed from lobe-finned fish continue to strengthen and support more weight on land. Bones become more defined and aligned in ways that improve stability and movement. These changes allow early tetrapods to move more effectively across uneven surfaces. The joints within these limbs provide increased flexibility, allowing for more controlled movement. This flexibility makes it possible to navigate obstacles such as vegetation, rocks, and soft ground. Improved movement expands the range of environments these organisms can explore. Despite these advances, early tetrapods remain closely tied to water for reproduction and protection. Their eggs require moist conditions, limiting how far they can move away from aquatic environments. This dependence keeps them near rivers, lakes, and wetlands. These environments provide both opportunities and challenges for early tetrapods. The presence of water supports their life cycle, while the surrounding land offers new sources of food and space. This combination encourages gradual movement between environments. As these organisms spend more time on land, their sensory systems begin to adapt to different conditions. Vision becomes more important in air, where light behaves differently than in water. Hearing also begins to change as organisms respond to sounds carried through air rather than water. The skin of early tetrapods must also adapt to prevent excessive water loss in dry conditions. While still dependent on moist environments, these organisms begin to develop features that help them survive outside of water for longer periods. These changes represent early steps toward full terrestrial life. On land, arthropods continue to provide a primary food source for early tetrapods. These small organisms are abundant and relatively easy to capture. This creates a connection between aquatic vertebrates and terrestrial ecosystems. Predation on land introduces new interactions between species, contributing to the development of food webs. Early tetrapods become both predators and prey within these systems. These interactions drive further adaptation and specialization. The structure of terrestrial ecosystems continues to grow more complex as plants and animals interact in new ways. Forests provide shelter and resources that support a variety of organisms. These environments create stable conditions that encourage further diversification. Soil systems continue to develop as organic material is broken down and recycled. This process supports plant growth and contributes to the stability of ecosystems. The interaction between plants, soil, and microorganisms remains essential. The connection between land and water remains strong as early tetrapods moved between these environments. Nutrient flow, atmospheric changes, and water movement link these systems together. This interconnectedness influences how ecosystems develop. Marine environments also continue to evolve as species adapt to changing conditions. Fish that can move efficiently and adjust to different food sources remain successful. These adaptations allow them to persist in environments that are still recovering from earlier changes. Cartilaginous fish continue to play a major role as predators in marine ecosystems. Their efficient movement and sensory awareness allow them to locate prey in a variety of conditions. These traits support their continued success. Bony fish remain diverse and adaptable, occupying a wide range of ecological roles. Their ability to adjust to different environments allows them to survive in both stable and changing conditions. This flexibility contributes to their long-term persistence. The interaction between marine and terrestrial systems continues to shape the global environment. Changes in one system can influence the other through nutrient flow and atmospheric conditions. These connections create a unified system that supports life. As ecosystems stabilize, the processes of adaptation and diversification continue to drive evolution. Organisms respond to environmental pressures by developing new features and behaviors. These changes contribute to the ongoing development of life. The expansion of life onto land represents a major shift in the history of vertebrates. Early tetrapods demonstrate how organisms can adapt to new environments and take advantage of new opportunities. This transition continues to influence future development. The Devonian period, although ending, leaves a lasting impact on the structure of life. The innovations that occur during this time, including limbs and complex ecosystems, continue to shape evolution. These developments provide a foundation for future changes. As life continues to evolve beyond the Devonian, the systems that developed during this time remain important. The connections between organisms and their environments continue to influence how ecosystems function. These patterns remain central to the process of evolution. The movement of vertebrates onto land, combined with the continued development of marine life, demonstrates the adaptability of life on Earth. Organisms continue to respond to changing conditions and explore new environments. This process drives the ongoing expansion of life. The changes that began during the Devonian continue to influence the direction of evolution in later periods. The structures and relationships that formed during this time remain present in future ecosystems. These connections ensure continuity in the development of life. As early tetrapods continue to adapt, their role within terrestrial ecosystems becomes more significant. Their presence introduces new interactions and pressures that shape the environment. These changes contribute to the ongoing increase in land complexity. The Devonian transition marks the beginning of a new phase in the history of life, where land and water are both important environments for vertebrates. The ability to move between these environments creates new opportunities for survival and adaptation. This shift represents one of the most important developments in the evolution of life. As vertebrate life continues to expand beyond water, the environments along the edges of rivers, lakes, and wetlands become some of the most important areas for development. These boundary zones provide access to both aquatic and terrestrial resources, allowing organisms to move between environments. This flexibility supports survival in conditions that continue to change. These transitional environments are often rich in plant life, creating dense areas of vegetation that provide shelter and food. The presence of water ensures that conditions remain moist, which is necessary for early tetrapods that still depend on hydration. This combination of features makes these areas ideal for continued adaptation. Movement within these environments requires control and stability, as the ground is often uneven and soft. Early tetrapods use their limbs to push against the ground and navigate obstacles such as roots and debris. This type of movement is different from swimming and requires coordination and strength. As these organisms spend more time on land, their muscles and skeletal structures continue to develop in ways that support weight and movement. Stronger limbs allow for longer periods outside of water, while improved coordination helps in navigating complex terrain. These changes expand the range of environments that can be explored. Feeding behavior also begins to shift as new food sources become available on land. Arthropods provide a consistent source of nutrition, and their presence encourages tetrapods to remain in terrestrial environments for longer periods. This interaction strengthens the connection between vertebrates and land-based ecosystems. Predation becomes more common on land as vertebrates begin to hunt smaller organisms. This introduces new pressures within terrestrial ecosystems, influencing how species behave and adapt. These interactions contribute to the development of more complex food webs. At the same time, early tetrapods must avoid becoming prey themselves, as larger organisms may take advantage of their presence. This creates a balance between hunting and avoiding danger. Survival depends on the ability to respond quickly to changing conditions. The development of sensory systems continues to play a key role in this process, as organisms adapt to detecting signals in air rather than water. Vision becomes more effective for spotting movement at a distance, while other senses adjust to new environmental conditions. These changes improve awareness and response. The skin of early tetrapods continues to adapt, helping to reduce water loss while still allowing for necessary exchange with the environment. Although these organisms remain dependent on moist conditions, these adaptations allow them to spend more time on land. This represents another step toward full terrestrial life. On land, plant life continues to create structured environments that support a variety of organisms. Forests provide shade, moisture, and protection, creating stable conditions for life to develop. These environments become increasingly important as more species move onto land. Soil systems continue to support plant growth and provide a foundation for ecosystems. The breakdown of organic material releases nutrients that are used by plants, creating a cycle that supports continued development. This process is essential for maintaining healthy environments. Arthropods continue to play a central role in terrestrial ecosystems, interacting with both plants and other organisms. Their presence contributes to decomposition, predation, and the cycling of nutrients. These interactions help maintain balance within ecosystems. Marine environments also continue to evolve as species adapt to changing conditions. Fish that are able to move efficiently and adjust to different food sources remain successful. These adaptations allow them to persist in environments that continue to change. Cartilaginous fish continue to function as effective predators, using their movement and sensory abilities to locate prey. Their presence influences the behavior of other species and contributes to the structure of marine food webs. These interactions remain important. Bony fish maintain their diversity and adaptability, occupying a wide range of ecological roles. Their ability to adjust to different environments supports their continued success. This flexibility remains a key factor in survival. The connection between land and marine systems remains strong, as processes in one environment continue to affect the other. Nutrient flow, atmospheric conditions, and water movement link these systems together. This interconnectedness continues to shape ecosystems. Atmospheric conditions continue to influence life by affecting temperature, moisture, and oxygen levels. These factors determine where organisms can survive and how they interact. Changes in these conditions require ongoing adaptation. As ecosystems continue to develop, interactions between species become more structured and predictable. These interactions include competition, predation, and cooperation, all of which influence how organisms evolve. This structure contributes to the stability of ecosystems. The expansion of life onto land continues to represent a major shift in the history of vertebrates. Early tetrapods demonstrate how organisms can adapt to new environments and take advantage of new opportunities. This transition continues to influence future development. The Devonian legacy remains visible in the systems that continue to evolve beyond this period. The structures and relationships that form during this time continue to influence life. These patterns remain central to the process of evolution. As early tetrapods continue to adapt, their role within terrestrial ecosystems becomes more established. Their presence introduces new interactions and pressures that shape the environment. These changes contribute to increasing complexity on land. The ability to move between water and land provides a significant advantage in environments that continue to change. This flexibility allows organisms to respond to different conditions and access a wider range of resources. This adaptability supports long-term survival. The environments along the edges of water bodies continue to serve as important centers for evolution, where new adaptations can develop. These areas provide the conditions needed for continued change and interaction. They remain central to the development of life on land. As these processes continue, the movement of vertebrate life onto land becomes more established, setting the stage for future developments. The changes that began during the Devonian continue to influence life long after the period ends. These developments represent a key stage in the history of evolution. As vertebrate life becomes more established along the edges of land and water, the interaction between organisms and their environments continues to shape new patterns of survival. These boundary regions remain central to development, providing access to both aquatic and terrestrial resources. The ability to move between these environments continues to offer advantages as conditions change. Early tetrapods begin to show more consistent use of land, even though they remain dependent on water for reproduction. Their limbs provide greater support and allow them to move with more control across uneven terrain. This improvement in movement expands the range of environments they can explore. The skeletal structure of these organisms continues to strengthen, allowing for better support of body weight outside of water. Bones become more defined, and joints allow for more precise motion. These changes contribute to increased stability and coordination on land. Muscles also develop to support these new forms of movement, working with the skeletal system to produce controlled motion. This coordination allows early tetrapods to navigate obstacles such as vegetation, rocks, and soft ground. Movement becomes more efficient as these systems improve. As these organisms spend more time on land, their behavior begins to reflect the conditions of terrestrial environments. They must respond to factors such as temperature changes, moisture levels, and exposure to air. These conditions require ongoing adaptation. Feeding continues to play a major role in the expansion of life onto land, with arthropods providing a reliable source of food. The presence of abundant prey encourages tetrapods to remain in terrestrial environments for longer periods. This strengthens the connection between vertebrates and land-based ecosystems. Predation becomes more established on land as vertebrates interact with smaller organisms. This introduces new dynamics within ecosystems, as species must adapt to both hunting and avoiding being hunted. These interactions contribute to increasing complexity. The development of sensory systems continues as organisms adapt to detecting signals in air. Vision becomes more important for locating prey and navigating environments, while other senses adjust to new conditions. These changes improve awareness and response. Skin adaptations help reduce water loss, allowing organisms to survive longer outside of aquatic environments. Although still dependent on moisture, these changes support greater independence from water. This represents another step toward fully terrestrial life. Plant life continues to influence terrestrial environments by providing structure, food, and stable conditions. Forests create shaded areas with consistent moisture, supporting a variety of organisms. These environments remain important for continued development. Soil systems continue to support plant growth and provide a foundation for ecosystems. The breakdown of organic material releases nutrients that sustain plant life. This process contributes to the stability of terrestrial environments. Arthropods continue to diversify and occupy different roles within these ecosystems, interacting with plants and other organisms. Their presence supports decomposition, predation, and nutrient cycling. These interactions maintain balance within the system. Marine ecosystems also continue to evolve as species adapt to changing conditions. Fish that are able to move efficiently and adjust to different food sources remain successful. These adaptations support survival in dynamic environments. Cartilaginous fish continue to function as effective predators, using their sensory abilities to locate prey. Their presence influences the behavior of other species and contributes to the structure of marine ecosystems. These interactions remain important. Bony fish maintain their diversity and adaptability, occupying a wide range of ecological roles. Their ability to adjust to different environments supports their continued success. This flexibility remains a key factor in survival. The connection between land and marine systems remains strong, as processes in one environment influence the other. Nutrient flow, atmospheric conditions, and water movement link these systems together. This interconnectedness continues to shape ecosystems. Atmospheric conditions continue to influence life by affecting temperature, moisture, and oxygen levels. These factors determine where organisms can survive and how they interact. Changes in these conditions require ongoing adaptation. As ecosystems continue to develop, interactions between species become more structured and predictable. These interactions include competition, predation, and cooperation, all of which influence how organisms evolve. This structure contributes to the stability of ecosystems. The expansion of life onto land continues to represent a major shift in the history of vertebrates. Early tetrapods demonstrate how organisms can adapt to new environments and take advantage of new opportunities. This transition continues to influence future development. The patterns established during the Devonian, including adaptation, interaction, and environmental connection, remain central to the process of evolution. These patterns guide how organisms respond to changing conditions. They continue to shape the direction of life. As early tetrapods become more capable on land, their role within terrestrial ecosystems continues to grow. Their presence introduces new interactions and pressures that influence other species. These changes contribute to increasing complexity on land. The ability to move between water and land provides a significant advantage in environments that continue to change. This flexibility allows organisms to respond to different conditions and access a wider range of resources. This adaptability supports long-term survival. Boundary environments between land and water remain important centers for evolution, where new adaptations continue to develop. These areas provide the conditions needed for ongoing change and interaction. They remain central to the expansion of life onto land. As these processes continue, the transition of vertebrate life onto land becomes more established, setting the stage for future developments. The changes that began during the Devonian continue to influence life long after the period ends. These developments represent a key stage in the history of evolution. As the transition from the Devonian continues to influence life, the long-term effects of earlier changes become more visible in how ecosystems are structured. The interactions between organisms, environments, and resources now operate within systems that are more connected than before. These connections shape how life continues to develop. Marine ecosystems, which were reshaped by earlier extinction events, begin to show signs of stabilization under new conditions. Species that survived are now more evenly distributed across different habitats. This distribution supports the gradual rebuilding of food webs. In open water environments, fish that can move efficiently and adapt to changing conditions remain dominant. Their ability to travel long distances allows them to access resources that may be unevenly distributed. This mobility contributes to stability within marine systems. Cartilaginous fish continue to function as important predators, using their sensory systems to detect prey and navigate the environment. Their ability to respond quickly to changes in their surroundings supports their continued success. These traits allow them to occupy a wide range of roles. Bony fish maintain their diversity and adaptability, continuing to occupy many ecological niches. Their structural flexibility supports different feeding strategies and movement patterns. This versatility allows them to persist in both stable and changing environments. The interactions between predators and prey become more structured as ecosystems stabilize. Organisms develop more consistent behaviors based on their roles within the system. These behaviors contribute to the overall balance of ecosystems. Some species continue to specialize, focusing on specific resources or habitats. This specialization increases efficiency in stable environments, but may reduce flexibility. The balance between specialization and adaptability remains important for survival. On land, ecosystems continue to expand and develop as plant life remains a dominant force in shaping the environment. Forests provide stable habitats that support a growing variety of organisms. These environments encourage further diversification. Soil systems continue to support plant growth and contribute to the stability of ecosystems. The breakdown of organic material releases nutrients that sustain plant life. This process remains essential for maintaining healthy environments. Arthropods continue to diversify and occupy a wide range of roles within terrestrial ecosystems. Some feed on plants, others act as predators, and many contribute to decomposition. These interactions support the structure and function of food webs. Early tetrapods continue to develop their ability to move on land, becoming more effective in navigating terrestrial environments. Their limbs provide support and allow them to explore new areas. These changes represent continued progress in the transition to land. Although still dependent on water for reproduction, these organisms begin to spend more time on land. This increased presence leads to more interactions with other terrestrial species. These interactions contribute to the development of more complex ecosystems. The connection between land and marine environments remains strong as processes in one system continue to influence the other. Nutrient flow from land affects marine productivity, while atmospheric conditions influence both environments. This interconnectedness continues to shape life. Atmospheric conditions continue to evolve as plant life influences the balance of gases. Increased oxygen levels support more active organisms, while changes in carbon dioxide influence climate. These factors affect where organisms can survive. Climate patterns continue to shift gradually, influencing temperature, moisture, and the distribution of species. Organisms must adapt to these changes to survive. Adaptation remains a key factor in long-term success. As ecosystems stabilize, the interactions between species become more predictable and organized. This organization supports the flow of energy through food webs and contributes to overall stability. Stable systems are better able to support diverse life. Marine ecosystems continue to evolve as species adapt to changing conditions and expand into new roles. Open water remains central, while localized structures may develop over time. These changes contribute to ongoing development. On land, the expansion of plant life and the presence of early animals create conditions that support increasing biodiversity. These ecosystems become more stable and interconnected. The foundation for future terrestrial life continues to strengthen. The processes of adaptation, interaction, and environmental connection that developed during the Devonian continue to influence life beyond that period. These processes remain central to evolution, They guide how organisms respond to changing conditions. As life continues to evolve, the systems that emerged from the Devonian provide a framework for future development. The interactions and structures that form during this time influence later ecosystems. These connections ensure continuity in the history of life. The stabilization of ecosystems following periods of change demonstrates the ability of life to adjust and persist. Even after disruption, organisms find ways to survive and adapt. This resilience remains a defining feature of life on Earth. The legacy of the Devonian is seen in the continued development of complex ecosystems and the expansion of life into new environments. The patterns established during this time continue to influence the direction of evolution. Life remains dynamic and responsive as it moves forward. As these patterns continue, the influence of the Devonian becomes less about specific species and more about the systems that were created. These systems continue to evolve and support life in changing environments. The connections formed during this time remain central to the development of life. As the Devonian period reaches its conclusion, the full impact of its changes becomes clear in the structure of life on Earth. What began as a world dominated almost entirely by marine organisms has expanded into a system where land and water are closely connected. These connections continue to shape how life develops beyond this point. Marine ecosystems, once defined by large reef systems and highly specialized organisms, have adapted to new conditions following periods of environmental change. The loss of some groups has led to the expansion of others, creating a different balance within the ocean. This balance supports continued interaction and development among surviving species. Fish remain a central part of marine ecosystems, with both cartilaginous and bony fish continuing to occupy a wide range of ecological roles. Their ability to adapt to different environments and feeding strategies allows them to persist through changing conditions. These traits ensure their continued presence in future ecosystems. Cartilaginous fish continue to function as effective predators, using efficient movement and sensory awareness to locate prey. Their success is tied to their ability to respond quickly to environmental changes. These characteristics allow them to remain important members of marine systems. Bony fish continue to diversify, supporting a wide range of behaviors and feeding strategies. Their adaptability allows them to occupy different habitats and respond to varying conditions. This flexibility contributes to their long-term success. The structure of marine food webs continues to stabilize as interactions between species become more organized. Predators and prey develop consistent behaviors that support balance within ecosystems. These patterns allow energy to move efficiently through the system. On land, the expansion of plant life has transformed the environment into one capable of supporting a wide variety of organisms. Forests provide structure, food, and stable conditions that encourage further development. These ecosystems become the foundation for future terrestrial life. Soil systems, built through the accumulation and breakdown of organic material, continue to support plant growth and maintain environmental stability. The interaction between plants, soil, and microorganisms creates a cycle that sustains life on land. This process remains essential for ecosystem health. Arthropods continue to play a central role in terrestrial ecosystems, contributing to decomposition, predation, and nutrient cycling. Their presence supports the structure of food webs and helps maintain balance within the environment. These interactions are key to the continued development of life on land. Early tetrapods represent one of the most important developments of the Devonian, marking the movement of vertebrate life onto land. Their limbs, derived from lobe-finned fish, allow them to navigate terrestrial environments. Although still connected to water, their presence on land introduces new possibilities. As these organisms continue to adapt, they begin to spend more time on land, interacting with other terrestrial species. These interactions contribute to the development of more complex ecosystems. The transition from water to land becomes increasingly established. The connection between land and marine environments remains a defining feature of this period. Nutrient flow, atmospheric changes, and water movement link these systems together. These connections ensure that changes in one environment affect the other. Atmospheric conditions, influenced by the expansion of plant life, continue to shape climate and environmental conditions. Increased oxygen levels support more active organisms, while changes in carbon dioxide affect temperature. These factors influence where species can survive and how they interact. Climate patterns continue to shift gradually, influencing ecosystems across both land and sea. Organisms must adapt to these changes in order to survive. This need for adaptation drives continued evolution. The Devonian period demonstrates how life can expand, adapt, and reorganize in response to both opportunity and challenge. The development of jaws, limbs, and complex ecosystems creates a foundation for future change. These innovations remain important in later periods. The extinction events that occurred during the Devonian highlight the vulnerability of complex systems to environmental change. At the same time, they show how life can recover and continue to evolve. The balance between growth and disruption remains central to the history of life. As the period ends, the systems that have developed continue to evolve under new conditions. Surviving species expand into available niches and begin to diversify. This process leads to the development of new ecosystems. The legacy of the Devonian is seen in the continued evolution of life across both marine and terrestrial environments. The patterns established during this time continue to influence how organisms interact and adapt. These patterns remain central to the process of evolution. The movement of life onto land, combined with the continued development of marine ecosystems, represents one of the most important transitions in Earth's history. This shift creates new opportunities and challenges for living organisms. These developments shape the future of life. As ecosystems continue to stabilize and grow, the complexity that began during the Devonian continues to increase. Interactions between species become more refined, and systems become more interconnected. These changes support the continued expansion of life. The Devonian period, although distant in time, provides insight into how life responds to change and adapts to new environments. The processes observed during this time continue to operate in later periods. These processes drive the ongoing development of life. The world that emerges from the Devonian is one where life is no longer limited to the ocean, but extends across land and water in interconnected systems. This expansion sets the stage for future developments that will continue to shape the history of life on Earth. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about the Devonian period.